people. Figured I'd entertain you for a second there with my my intro music. And today we're going to be exploring exponential models, and we are going to be looking at a couple formulas. And the first one I'm going to show you is y equals a times b to the x. And there's a couple things about this formula I want to show you. The first thing is that if a is greater than 0, and 0, and b is greater than 1, it is exponential growth. Should have written this like inequality. Anyway, next part is if a is greater than 0, and b is between 0 and 1, it is exponential decay. All right, so exponential growth is where something gets bigger and bigger and bigger, and exponential decay is where it gets smaller and smaller and smaller. Okay, that's the general idea. So you can tell if you have an equation whether it's exponential growth or decay just by looking simply at what b is. Usually a is greater than 1. But if I gave you, for example, an equation where it was y equals 2 times 3 to the x, and I asked you whether it's exponential growth or decay, you would look at it and say, gee, 3 is greater than 1, therefore it's exponential growth. And if it was between 0 and 1, it would obviously be exponential decay. All right, next. If I gave there's another equation I'm going to give you. Oh, one more thing on that is the y-intercept. Move this down a little bit. Sorry about that. Is the y-intercept is 0a. Back to black. Okay, next. This is another equation, and they're similar. In fact, they're almost the same. One of them has to do with rates. The first one I showed you was a regular exponential growth or decay kind of equation. This is the one where it's y equals a times 1 plus r to the t power, and y is the total amount. A is the initial amount. R is the rate of growth. Or decay. And it would be growth if R is greater than 0, and it's decay if R is less than 0. And the last thing is, with this equation, is t. And t is the number of time periods. Okay, so that's the equation. Those are both of them. Make sure you got them written down. And I'm going to kind of give you an idea of what these look like on a graph. So quickly, I'll come back to this in a minute. I'll try not to worry about you guys keeping up. You can always hit rewind. All right, so if I go to my graphing calculator for a moment, and I was to graph y equals 2 to the x power, y equals 2 exponent x. So I put the exponent in the variable, the variable in the exponent, and you can see that this keeps getting bigger and bigger. And if I scroll out a little bit, you can see these exponential growth numbers get huge really fast. There's different kinds of growth in the math world, and exponential is the fastest. So that's what y equals 2 to the x would look like. Now if I was to show you one with exponential decay, which would be going the other direction, I'll do y equals 2 times 1/2 to the x, for example. Y equals 2 times, this needs to be in parentheses, 0.5 to the x. And you can see that it grows, this one shrinks. Sorry, the red one is the exponential growth, which gets bigger and bigger, and the blue one is the exponential decay, which gets smaller and smaller and smaller. These curves, they approach the x-axis from opposite directions, but they never actually get there, which is, we call that an asymptote in math, and we can talk more about that later, but that's what that is. You know, these lines would be, the x-axis right along here would give you our points that they will never reach. They'll keep getting closer and closer and closer, but never reach there. Okay, so that's two examples, one of each, generally what the graphs will look like. We'll do more with the graphs later, but I just wanted to show you so you can see what we're dealing with. Excuse me. All right, back to my my notes here. If I go down, that's okay. So a lot of these are word problems, which is kind of cool because a lot of these I like. They have to do with money. I like money. I like real world kind of problems. So I'm just going to kind of jump in. This guy got some word problems to tackle with you guys. The first one is you invest $1,000 in a savings account. That pays 5% annual interest. How much money will be in the account after 6 years? Okay. So we're going to use that second formula. This is a rate problem because it's got the 5% in there, as you can see. And the second one, the y equals a times 1 plus r to the t power is the one we use with these rates. Right? Now there is actually a compound interest equation which would be more accurate for this, and I'll show you that later on in the year. I forget exactly when, but anyway, we'll get to that. For now, I'm going to go like this. I'm going to use that equation, y equals a times 1 plus r to the t, and I'm going to need to plug these values in. So a is the initial amount. The initial amount was the $1,000 that I invested. R is the rate, and it has to be in decimal form, all right? Which means this is 5%, but that's actually going to be 0.05 when you take 5%. That here, 5% equals 0.05, right? Divide by 100 or move the decimal point 2 to the right. So that's my rate, and t is going to be 6. Okay, so now if I plug those numbers into my equation, I get y equals 1 plus, and I'm going to plug in those three numbers over here. I got 1,000, 1,000. 1 plus r is 0.05, and to the 6th power. Okay, and then you're going to take your handed-in calculator and go 1.05 to the 6th power times 1,000 and get your answer. And in this case, the answer turns out to be $1,340.10. So if they asked you how much interest you made, you start out with $1,000 and you ended up with $1,340, so you gained $1,340 and, oh, sorry, you gained $3,340.10. If you took the 1,000 and subtracted the 1,340, or vice versa, rather, you'd get just the amount of interest. Okay, that was the first one. 2. Your credit card charges 1.25% per month interest. Boy, is that low interest rate for a credit card. Your credit card charges 1.25% interest per month. How much will you you owe $4,000. How much will you owe after one year? All right, next. So here we go. I'm going to plug these values in. I'm going to use that same formula. This is once again is a rate kind of problem. There's the percentage, which is my interest rate, and so R. If I take that number and move the decimal point 2 to the left, which is the same as dividing by 100, I get 0.0125. And A is the initial amount, which is 4,000, which is the amount of the loan. And I'm going to plug this into that formula. Y equals A times 1 plus R to the T power. And when I do plug these numbers in, I get 4,000 times 1 plus 0.025 is 1.025 to the T power, and they said 1 year, so T is 1. All right, so here we go. Now I'm going to punch this into my calculator. Anything in the first power is itself, so I'm actually taking 1.025 and multiplying it by 4,000, and that should give me my answer of $4,100. And that was a ridiculously low interest rate. You will never see a credit card with an interest rate that low, I doubt, unless it's for a short period of time. Usually they're up around 10% to 15% or higher. Anyway, we'll talk more about real-world credit card issues later on in class. So that was number 2. Number 3. Here, why don't you try this one? You put $25,000. It's been a good week. 25 grand in a bank account. That earns 6% interest per year. How much money will be in the bank account after 3 years? And you assume you don't take any money out during the 3 years. Okay, so you should probably hit pause right now on your thing and do it out, see if you can come up with the answer. Okay, and so hit pause now, and then when you're done, come back, because I'm going right through. I'm not going to hit pause. All right, so if I do this out correctly, I got the initial amount is 25,000. 1 plus R is 0.06 to the third power. Punch that into your calculator. Your answer. Third. Make sure you do the exponent first and then multiply. That's the easiest mistake to make. Okay, I see kids who do these problems and then they write down their answer and they go, they multiplied by 25,000 and they get 25 million or something. And I said, geez, That would be really nice. I'd love to take $25,000, put it in the bank account, and come back 3 years later and be a millionaire many times over, but that's not the way the real world works. So check and see, does your answer actually make sense? You don't usually make that much money on interest. I mean, the more money you put in there, the more you get. In this case, I made like almost $5,000 in interest in 3 years, and that's pretty good. 6% is a high interest rate too for real world. All right, so there's that one. I'm going to do a population one now. Next question is 4. A population of 1,200 grows 3% per year. For 5 years. What's the population after 5 years? Okay, so I'm going to use that same equation. It's y equals the initial amount. In this case, it's 1,200. It doesn't say what it is. It could be people. It could be frogs. But it's 1,200 of some kind of population, and it grows. And once again, we have to think about, don't plug in 3 because you'll get a much bigger number than you want. 3% is 0.03, so that's the one I'm going to use. And the number of years is 5, so that's what goes here. All right. So now I'm going to punch the numbers in my calculator. Once again, do the addition first, and then do the exponent. Remember, order of operations, PEMDAS. Exponents comes before multiplication. So 1.03 to the 5th power is 1.15. Write that step down this time. 1.15927 times 1,200 comes out to 1391.13. So you'd probably round off. It's a population. You're assuming that it is some kind of living thing, so it's tough to have 0.13 people or 0.13 frogs, and we don't have to have that discussion about how you get that. But anyway, we'll say 1391, okay? Can you have 0.13 frogs? All right, anyway, next. Then we're going to do a population decrease one next. I got number 5 next. The population of 60,000 decreases by 20% for 4 years. By 20% for 4 years. What's the new population? With the real world applications. All right, so you can think of a town that's getting smaller by 20% every year, which isn't 80%. You'd think it is, but it's actually not, because it's 20%, and then you have less people, and it's 20% of that, which is different than, it's not 20% times 4, as you'll see in a minute. So, all right, so next I'm going to use the formula. Y equals, the initial amount is 60,000, so that goes in the front, and then I got 1. Now here's the difference. This is easy. This is the 4 there. Now the rate, since it's going down, I'm actually going to go 20%. Change colors. 20% is 0.2. Okay, so hopefully you're okay with that. And so, but it's going down, so I'm going to go minus 0.2 instead of plus 0.2 there. Okay. Seems to be a little program's not keeping up. There's lag or something here. So anyway, there it is. All right, so minus 0.2 instead of plus 0.2 because it's going down. You could also think of this, if it decreases by 20%, there's 80% left, which is what you're going to get in a moment when I do that subtraction of 0.2 from 1, which is also 80%. So either way, you get that, okay? And once again, make sure you do the exponent first, and it's calculator work from here on out. Please bring a calculator. It'd be rather excruciating to have to do 0.8 to the 4th power times 60,000 with no calculator. So I got y equals 24,576. And once again, they didn't tell us what kind of population it is, just that it is one. All right, so there's their population decay. All right, so let's backtrack just for 1 second. Here's the easy one for you. Once you tell me, I'm on question 6, is this represent growth or decay? Exponential growth or decay? It's y equals 100 times 0.6 to the x. So hit pause, think about it, write down your answer, and then come back. And I'm back. So if I look at this, it is the initial amount's 100. It's the 0.6 here that is determining whether it's growth or decay. Since it's between 0 and 1, it is exponential decay. If that number was greater than 1, it would be exponential growth. Okay, so I think I'm going to wrap things up here. All right, and you know, I figured I'd put this up here just quickly. You know, if the holidays are coming up soon, and that's not it. And if you're looking for, oh no, maybe I can't find it now. Oh well, that's too bad. Oh well, all right. So I guess I am wrapping things up. So I'll save that comment for the next video, whenever that is next week. So see you all in class tomorrow. Have a great night. Bye.